The solar system operates on a single, crowded floor. Almost all human space activity, natural bodies, and transfer arcs are trapped in a dense, zero-degree horizontal band known as the ecliptic plane. While space itself is vast, our operational use of it is not. Practically speaking, orbital mechanics compress our trajectories into a tightly packed, increasingly hazardous horizontal corridor. The instinctive solution is to simply build further out, but moving further along the exact same geometric plane does not solve the underlying congestion problem. Dispersing nodes laterally merely spreads the risk across a wider, flat surface. Transfer corridors and servicing lanes will still constantly intersect, creating an endlessly compounding traffic jam of spacecraft and orbital debris. Launch capability has reached maturity. The current bottleneck is infrastructure continuity. Expanding further requires a logistics network capable of surviving long-term operational stress. Without introducing an entirely new spatial geometry, our off-world logistics networks will eventually buckle under the weight of their own unmanaged congestion. Gerald Welch views orbital development through the lens of a systems thinker and infrastructure conceptualist, focusing on the underlying logic of civilization architecture. His earlier work on unified spacetime established a methodology focused entirely on operational continuity and the logic of large-scale, long-term civilization architecture. The Archer program is his structural answer to escaping the compounding risks of the ecliptic plane. The program's name evokes historical pathfinders, vessels like the Nautilus or early NX-era concepts, which represented a civilization's initial, uncertain entry into a new operational domain. These proposed stations are not meant to be the final form of human off-world settlement. They are the strictly functional, transitional infrastructure required to make that eventual settlement possible. The logic is straightforward. Survival requires us to construct durable, permanent systems long before our daily operations actually depend upon them. This schematic illustrates the core Archer concept, distributing solar infrastructure vertically along the z-axis, creating clear layers far above the congested ecliptic plane. The architecture begins here, at the Archer 1 validation layer, positioned exactly 2 degrees superecliptic. Placing a node at this inclination demands only a low delta-V premium from launch vehicles. Its purpose is strictly functional, to measure actual orbital traffic density and validate robotic maintenance protocols in a slightly offset environment. Moving higher, we reach Archer 2 at 4 degrees superecliptic. This serves as the first fully operational logistics backbone node. Pushing to 4 degrees requires a moderate increase in access cost, but in exchange, it guarantees substantial operational isolation and structural traffic segregation. It functions as a safe staging ground for nuclear servicing, thermal management, and emergency response, deliberately removed from the civilian corridors below. Distributing these operations vertically is the only mathematical way to break the compounding risks of the ecliptic. It applies a structural solution to a structural problem. Beyond logistics lies the requirement for absolute strategic isolation, where critical infrastructure operates entirely outside the reach of routine human access. This chart shows the Century nodes, stationed at an extreme inclination of 7 degrees superecliptic and beyond. Reaching this tier requires an aggressively high delta-V premium, demanding immense energy and resources to achieve an intercept. But that extreme cost is the point. The steep barrier to entry inherently buys maximum longevity and total separation from everyday solar traffic. These are hardened, restricted nodes designed exclusively to anchor deep system logistics and support long-duration missions without interference. At 7 degrees, the sheer emptiness of space itself is leveraged into a strategically defensible and survivable operational asset. Viewing the full schematic, the individual stations dissolve into a single, unified architectural philosophy. Welch calls this the Superecliptic zoning doctrine. By separating operational lanes spatially based on the cost to reach them, this framework organically creates civilian, strategic, and restricted zones. It requires no artificial enforcement mechanisms. Physics itself dictates the access. The Archer nodes function as distributed survivability systems, prioritizing robotic maintenance doctrine and logistics resilience over the requirements of human habitation. Their design is brutally practical. They rely on modular power grids composed of replaceable segmented tiles, minimal human command cells, and relentless, autonomous robotic maintenance. The historical spectacle of space exploration yields entirely to the quiet, unglamorous discipline of continuous operation. Building a durable presence in the solar system requires the discipline of a mature logistics network. The Archer program treats off-world expansion as a rigorous infrastructure problem. If we intend to survive as a durable, solar-scale civilization, we cannot rely on fragile ad hoc pathways. We have to build the road before the wagons.